The sun has been burning for nearly 5 billion years. It is so powerful that standing on Earth 93 million miles away, behind a thick atmosphere, it can still burn your skin in minutes. And yet the space surrounding it, in every direction, stretching out across the entire universe, is nearly the coldest thing that can physically exist. Not cool, not cold, nearly as cold gets. That should not make any sense. And for most of human history, it didn't. Think about every experience you have ever had with heat. A fire warms the room around it. An oven heats the kitchen. The closer you stand to something hot, the more you feel it. Heat spreads. Heat fills space. That is not an opinion. That is just what heat does. Except apparently not out there. Astronauts on the space station, just 400 kilometers above Earth, need full cooling systems to stop themselves overheating in direct sunlight, but drift into shadow just a few meters out of the light, and the temperature plunges to minus 160 degrees in minutes. The sun is right there. It is always right there. And somehow, it is not warming anything. This is not a gap in our knowledge. Scientists know exactly why this happens, but the explanation requires you to rethink something so fundamental, something so built into the way you experience the world every single day, that most people find it genuinely difficult to accept the first time they hear it. That is what this video is about. If this is the kind of question you've always wanted a real answer to, subscribe. There is a lot more of this coming. And if this one earns it, a like helps it find someone else who's been wondering the same thing. The question is simpler than it looks. The answer is not. We begin somewhere familiar, not in space, but in the quiet movement of matter around us. What we call heat is not an object you can hold or store. It is a behavior, a process unfolding at scales too small to see. Every surface, every breath of air, every solid object around you is made of particles in motion. Heat is simply the transfer of that motion, the passing of kinetic energy from one particle to another. When atoms and molecules collide, they exchange energy. Faster particles strike slower ones and share their movement. This chain reaction spreads outward, creating what we experience as warmth. Nothing is added. Nothing is created. Motion is simply redistributed. On Earth, this transfer follows three distinct paths. Conduction comes first, the direct contact between particles, like your hand touching a warm surface. Convection follows, where fluids like air or water carry energy as they move, rising, circulating, spreading heat through motion. Then there is radiation, energy traveling as electromagnetic waves, moving freely without needing contact or a flowing medium. All three shape your daily experience. A heated room, a boiling pot, sunlight on your skin. They work together so seamlessly that it feels natural to assume heat simply fills space. That assumption holds here, but it begins to break the moment we leave the ground. Because beyond the atmosphere, two of these pathways disappear entirely. Conduction requires particles touching. Convection requires a fluid medium to flow. In space, neither condition exists. There is no continuous matter to pass energy along, no air to rise, no currents to form, no chain of collisions to carry warmth outward. This brings us to the idea of a vacuum, not just empty in the casual sense, but a near-total absence of matter. In interplanetary space, you might find fewer than 5 atoms in a cubic centimeter. That is not thin air. That is almost nothing. With so few particles, there is nothing to collide, nothing to circulate, nothing to transmit motion between objects. Heat, as we experience it on Earth, loses its pathways. The mechanisms we rely on simply stop functioning. But one process remains. Radiation does not need matter. It moves as waves of energy. traveling across emptiness at the speed of light. It does not push through space the way air carries warmth. It crosses it silently, without interaction, unless something interrupts its path. This is where our intuition struggles. We expect energy moving outward to warm everything along the way, but radiation does not behave like spreading warmth in a room. It does not accumulate in the void. It passes through, unchanged, until it meets something capable of absorbing it. So the fire we imagined, the spreading heat we expect, never forms out there. The sun is releasing enormous energy. That much is certain. But without particles to carry or share that motion, the space around it remains untouched by the familiar flow of heat. And that leaves us with a precise question. When the sun's energy leaves its surface, what does it actually become? Before anything can warm, it must first be carried, not as heat, but as something more precise, more structured. What leaves the sun is not warmth in the form we recognize, but a stream of energy arranged across a wide electromagnetic spectrum. This spectrum is a continuous range of energy types, each defined by wavelength and frequency. At one extreme sit gamma rays, carrying immense energy in very short wavelengths. Then come X rays, followed by ultraviolet, visible light, infrared, and finally radio waves stretching across vast distances. The sun emits all of them at once, a layered output of radiation moving outward in every direction. But only a narrow portion of this spectrum feels familiar. Visible light and infrared radiation are the primary carriers of what we experience as warmth. Everything else passes unnoticed by human senses, though it still carries energy through space. This energy does not travel as a wave alone. It moves as photons, individual packets of light that carry specific amounts of energy depending on their wavelength. A photon has no mass, no rest weight, yet it moves at a constant speed of 299,792 kilometers per second. This speed does not change. It cannot slow down. From the surface of the sun, a photon begins a journey across empty space. It travels for 8 minutes and 20 seconds before reaching Earth. During that entire passage, it does not heat anything along the way. This is where the distinction becomes clear. Energy in motion is not the same as heat. Heat requires interaction, a transfer between particles. A photon moving through space is energy in transit, not energy being shared. It does not collide with air because there is none. It does not pass motion along because there are no particles to receive it. But the moment it encounters matter, everything changes. When a photon strikes a surface, it can be absorbed. Its energy is transferred into the atoms of that material, increasing their motion. That increase in motion is what we recognize as heat. Until that moment, the photon carries energy silently, without effect on its surroundings. This process is known as radiative energy transfer. It describes energy moving through space as electromagnetic radiation, only becoming heat when it interacts with matter. The key detail is simple but counterintuitive. Energy can exist without warming anything. Between the sun and Earth, countless photons pass through the darkness every second. They move through that space without raising its temperature. The vacuum does not store their energy. It does not accumulate warmth. It remains unchanged. So the region between star and planet stays cold, even as vast amounts of energy cross it continuously. But when those photons reach an object, whether a planet, a surface, or even a thin layer of gas, their journey ends in transformation. Motion becomes shared. Energy becomes heat. And with that shift, the paradox begins to loosen. A fraction arrives, and everything changes. Out of the sun's vast output, only about 0.00000 0.045% reaches Earth. That small share is enough to power oceans, weather, and every living system you know. When this energy meets the planet, it does not pass unnoticed. It encounters an atmosphere, a layered envelope of gases that surrounds the surface. Nitrogen and oxygen dominate, with traces of water vapor and carbon dioxide. These molecules interact with incoming radiation, absorbing portions of it and then releasing energy again in new directions. This exchange begins the transformation from traveling energy into shared motion. The atmosphere does not simply let energy pass through, it participates. Some sunlight reaches the ground. Soil, rock, and water absorb incoming photons and convert that energy into internal motion. Surfaces warm, but they do not hold that energy silently. They emit it again as infrared radiation, a longer wavelength form that carries energy back upward. Now a different process begins. The air in contact with the surface gains energy and starts to move. Warmer air becomes less dense and rises, while cooler air sinks to replace it. This circulation is called convection, the movement of heat through a fluid driven by differences in temperature and density. It spreads warmth upward and outward, blending energy across layers of the atmosphere. At the same time, certain gases intercept the outgoing infrared radiation. They absorb it and release it again, some directed back toward the surface. This repeating exchange forms what we call a thermal trap, where energy is retained within the lower atmosphere rather than escaping freely into space. The result is not a single layer of warmth, but a dynamic system constantly redistributing energy. Surface, air, and radiation interact in continuous balance. You feel this as a stable climate, though it is anything but still. But rise high enough, and this system begins to fade. Around 100 kilometers above the surface, the atmosphere thins to the point where its influence weakens sharply. Molecules become sparse, collisions become rare, convection slows, then nearly stops. Beyond this boundary, conditions shift entirely. In low Earth orbit, objects are exposed directly to incoming solar radiation. A surface facing the sun can reach temperatures around 120 degrees Celsius. Turn that same surface into shadow, and it can fall to negative 160 degrees Celsius within minutes. These extremes exist side by side on the same structure. But this is not because space itself has hot and cold regions. Each surface is responding independently to radiation. There is no surrounding medium to distribute energy evenly, no air to carry warmth from one side to another. Each exposed area absorbs energy only where light reaches it, and loses energy where it does not. Between these surfaces lies the vacuum, the same near-empty environment described earlier. It does not store heat, it does not average temperatures. It provides no baseline in the conventional sense. So while Earth holds warmth through interaction and exchange, the space just beyond remains untouched, unchanged, and fundamentally indifferent to the energy passing through it. Temperature sounds simple until we remove everything you can touch. It is not a property that exists on its own. It is a measure of motion, specifically how fast particles move and vibrate within a substance. Faster motion means higher temperature. Slower motion means lower temperature. Take away motion entirely, and you reach a limit. Absolute zero sits at negative 273.15 degrees Celsius. At this point, particle motion would theoretically stop. No vibration, no internal energy exchange, no thermal activity at all. It is not just cold, it is the absence of motion itself. But the universe never quite reaches that state. Even in the emptiest regions of space, a faint presence remains. It comes from the cosmic microwave background, often shortened to CMB. This is a form of radiation that fills the entire universe, arriving equally from every direction at every point in space. Its temperature is about 2.7 Kelvin. Kelvin is a temperature scale used in physics that begins at absolute zero, avoiding negative numbers entirely. 0 Kelvin represents no motion. 2.7 Kelvin means only a tiny amount of motion exists above that limit. Converted to Celsius, this becomes negative 270.45 degrees. That value defines the baseline temperature of deep space, not because space contains heat in a familiar sense, but because this radiation carries a faint, uniform energy. But this number needs perspective. 2.7 Kelvin is not nearly zero in everyday experience. It is almost zero in universal terms. It represents the leftover energy from a time when the universe was unimaginably hot and dense. What we measure today is the cooled remnant of that beginning, stretched and diluted over billions of years. This radiation does not gather or pool. It does not warm surfaces in any meaningful way. It exists as a background presence, setting the lowest measurable thermal floor across the observable universe. Wherever you go, it is there, even in vast regions far from stars where no direct energy source exists. This faint radiation defines the temperature. Objects placed in such regions will slowly release their own energy until they approach this level, settling into equilibrium with the background. But the story is not static. The universe has been expanding since its origin. As space stretches, the wavelengths of this background radiation stretch with it. Longer wavelengths mean lower energy. Over time, this baseline temperature continues to fall. 13.8 billion years ago, this same radiation was far hotter, dense enough to shape the formation of matter itself. Now it lingers at the edge of measurable cold, a quiet trace of an earlier state. So when we speak of space as cold, we are not describing an active condition, we are describing the default. Heat appears locally, briefly, wherever energy concentrates, but the underlying trend is always the same. The universe began hot, then expanded, and in doing so, it has been cooling ever since. Long before stars or planets existed, the universe passed through a moment of release. In its earliest phase, everything was compressed, hot, and opaque, a dense plasma where light could not travel freely. Particles collided constantly, scattering energy in every direction, trapping radiation within the chaos. Then, expansion began to change that condition. About 380,000 years after the beginning, temperatures dropped enough for electrons to bind with atomic nuclei. This process is called recombination, meaning charged particles combined to form neutral atoms for the first time. With fewer free charges to scatter light, the universe shifted from opaque to transparent. Light was finally able to move. What emerged was not a flash in the dramatic sense, but a steady release. Photons that had been trapped began traveling outward in all directions. That radiation did not vanish. It has continued moving ever since, stretching across expanding space, cooling as it goes. We can still detect it today. This ancient light is known as the cosmic microwave background, or CMB. It arrives uniformly from every direction, forming a faint but consistent signal that fills the observable universe. Wherever you look, it is present, carrying information from that early transition when matter and radiation first separated. Its discovery was not planned. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Laboratories with a sensitive microwave antenna. They detected a persistent noise that appeared identical in every direction. It did not vary with time or location. They considered equipment issues, even contamination, from birds nesting in the antenna. But the signal remained. What they had found was the CMB, the residual radiation from the early universe. Their accidental observation confirmed theoretical predictions about the universe's origin and provided direct evidence of its hot beginning. This radiation defines the baseline temperature of space. Without it, there would be almost no measurable thermal presence in the vast regions between stars. The CMB sets a floor, a faint but universal level of energy that prevents the universe from reaching perfect stillness. But it is not constant. As the universe expands, the wavelengths of this radiation stretch. Energy decreases, temperature drops. Over time, the CMB continues to cool, moving closer to absolute zero with each passing era. In about 1 trillion years, it will become nearly indistinguishable from that limit. This leads to a quiet shift in perspective. Space is not cold because something removed its heat. It is cold because that is its natural state after expansion. The early universe began in extreme heat, but that condition was temporary, tied to density and compression. As space grew, energy spread out, becoming thinner, less concentrated, less able to produce warmth. Heat emerges only where matter gathers and energy concentrates again. Everywhere else, the universe returns to its baseline, a vast, uniform cold shaped by time, expansion, and the fading echo of its beginning. Out of that quiet baseline, something gathers and refuses to stay cold. Across vast regions, thin clouds of hydrogen begin to draw inward under gravity, each atom pulled toward a common center. The process is slow, measured in millions of years, but it does not stop. Density increases, collisions become more frequent, motion builds. As particles compress, their kinetic energy rises, temperature follows. Eventually, conditions reach a threshold where a new process begins. Nuclear fusion. The combining of light atomic nuclei into heavier ones ignites when pressure and heat become extreme enough. This is how a star is born. Inside our sun, about 600 million tons of hydrogen are fused into helium every second. A small fraction of that mass converts directly into energy, released as radiation that moves outward through the star's interior layers. The core sustains the reaction. The outer layers respond. Energy produced at the center takes thousands of years to reach the surface, moving through dense plasma where particles remain tightly packed. When it finally escapes, it leaves as radiation, beginning the journey we have already traced. But notice the boundary. All of this activity is confined within the star itself. Fusion occurs only where density and pressure are high enough. The surrounding vacuum does not participate. It does not absorb the process or spread its effects. The star burns intensely, but only within its own structure. This makes every star a localized exception. The sun's surface, called the photosphere, maintains a temperature of about 5,500 degrees Celsius. Yet above this visible layer lies something unexpected. The corona, the sun's outer atmosphere, extends millions of kilometers into space and reaches temperatures between 1 and 3 million degrees Celsius, hotter than the surface below it. This reversal challenges simple intuition. Heat usually flows outward and cools with distance. Here, the outer layer is vastly hotter than the region beneath it. The mechanism behind this remains one of the major unresolved problems in solar physics. Several explanations exist. Magnetic reconnection is one leading idea, where twisted magnetic field lines snap and realign, releasing bursts of energy into the surrounding plasma. Another involves Alfvén waves, oscillations in magnetic fields that carry energy upward from the sun's interior into the corona. Both processes suggest that energy is being transported and concentrated in ways not yet fully understood. But even at these extreme temperatures, something remains unchanged. The corona's heat does not spread into space in the way we might expect. Its particles are incredibly energetic, but also extremely sparse. Without sufficient density, they cannot transfer energy effectively to anything beyond the sun's immediate influence. So the corona glows with intense heat, yet just beyond it, the vacuum remains largely unaffected. This pattern repeats everywhere. Stars generate extraordinary energy through fusion, shaping their own environments and illuminating nearby space. But the vast regions between them remain governed by the same low energy baseline. Heat appears where matter gathers and compresses. Everywhere else, the universe holds to its colder state, unchanged by even the most powerful sources of energy. Not all of the sun's influence travels as light. Some of it moves as matter, carried outward in a continuous stream that never truly stops. This flow is called the solar wind, and it begins in the outer layers of the sun, where particles gain enough energy to escape its gravity. These particles are charged, meaning they carry electric charge. Electrons, protons, and alpha particles, which are helium nuclei made of 2 protons and 2 neutrons, are all swept outward together. They move at speeds between 400 and 800 kilometers per second, forming a constant outward pressure that fills the solar system. Unlike radiation, this is material leaving the sunday. Each particle carries kinetic energy, motion that could in principle transfer heat if enough collisions occurred. But as the solar wind spreads outward, it becomes thinner. By the time it reaches Earth's orbit, the density drops to only about 5 to 10 particles per cubic centimeter. That is far too sparse. With so few particles, collisions become rare. Energy is not shared effectively. The solar wind passes through space as a diffuse stream, carrying energy but unable to concentrate it into measurable warmth. But it does not pass unnoticed. When these charged particles encounter Earth's magnetic field, they are redirected toward the polar regions. There, they interact with atoms in the upper atmosphere, transferring energy that excites those atoms into higher energy states. As the atoms return to their original state, they release light, creating the shifting colors of auroras. The effect is visible. The heat is not. Even here, energy is expressed through interaction, not through warming the surrounding vacuum. The atmosphere provides the medium required for that exchange to occur. But continue outward, and the solar wind weakens further. At the distance of Pluto, about 5.9 billion kilometers from the Sun, the particle density becomes so low that its influence is barely detectable. The stream still exists, but it is stretched thin across a vast volume, losing its ability to interact in meaningful ways. Eventually, it reaches a boundary, around 120 astronomical units from the Sun, where 1 astronomical unit is the average distance between Earth and the Sun. The outward pressure of the solar wind meets the inward pressure of interstellar space. This boundary is called the heliopause, the point where the sun's influence effectively ends. Beyond it, a different environment begins. In 2012, the spacecraft Voyager 1 crossed this boundary. Its instruments recorded a sharp drop in solar particles and a shift in surrounding conditions, confirming that it had entered interstellar space. The density changed, the temperature profile shifted, the sun's direct reach had stopped. But the cold did not increase because something new was added. It was already there. Inside the heliosphere, the region dominated by the solar wind, there is at least some interaction, some presence of particles moving outward. Beyond it, even that fades, leaving only the sparse medium between stars. So even the sun's material influence has limits. Light continues outward indefinitely, but matter slows, thins, and eventually yields to the surrounding environment. And beyond that boundary, the universe returns fully to its underlying condition, a vast, quiet cold shaped by almost nothing at all. Once energy escapes a star, it follows a path that does not bend or fade in the way we might expect. Each photon moves outward in a straight line, traveling at a constant speed that never changes. There is no slowing, no drifting. It continues forward unless something interrupts its path. A photon can travel for billions of years without losing its identity. It carries energy determined at the moment it was created, and in empty space, that energy remains intact. Nothing absorbs it. Nothing diminishes it through contact, but distance changes something else. As photons spread outward from their source, they do not cluster together. They disperse across a growing area, thinning out as they move farther away. This behavior follows what is known as the inverse square law, a relationship where energy per unit area decreases as distance increases. Double the distance, and the same energy is spread across 4 times the area. At Earth's orbit, the Sun delivers about 1,361 watts of energy per square meter. This value is called the solar constant, representing the average energy received from sunlight at that distance. Move outward, and the numbers drop quickly. At Mars, the energy falls to roughly 590 watts per square meter. At Jupiter, it declines to about 51 watts. At Neptune, far at the edge of the major planets, it reaches only around 1.5 watts per square meter. The energy is still there, but it is spread so thin that its effect becomes negligible. Extend this pattern beyond the solar system, and the sun's radiation becomes indistinguishable from the background. At the distance of the nearest star, the energy from our sun is effectively zero, not because it vanished, but because it has been diluted across an immense volume. But the photons themselves continue. Most of the energy the sun releases never encounters a planet, a moon, or even a grain of dust. These photons move through space indefinitely, crossing vast distances without interaction. They do not accumulate. They do not build warmth in the regions they pass through. They simply move. This is where expectation fails. We imagine energy spreading outward and gradually warming everything it touches. But in space, there is nothing to hold or share that energy. Without matter to absorb photons, there is no mechanism to convert their energy into heat. So the void remains unchanged. Energy passes through it constantly, yet leaves no lasting effect. The presence of photons does not raise the temperature of empty space, because temperature requires interaction between particles. And without those interactions, nothing happens. So the pattern becomes clear. A star emits energy in all directions, and that energy travels outward forever. It only becomes heat when it meets something capable of absorbing it. Everywhere else, it remains in motion, silent and unspent, crossing the universe without altering the cold that surrounds it. Step into sunlight without air, and the rules change immediately. What you feel on Earth does not translate beyond it, because the body depends on its surroundings to manage heat. Remove that surrounding medium, and familiar processes begin to fail. A spacesuit is not built to keep you warm. Its primary function is to remove heat. Inside the suit, your body continues to produce energy through metabolism, converting chemical energy into motion and internal warmth. On Earth, excess heat escapes through air, carried away by convection and assisted by evaporation of sweat. In a vacuum, those pathways disappear. There is no air to carry heat away. Sweat cannot evaporate into empty space in the same way. Without an active system to remove heat, your body would continue to warm itself, with nowhere for that energy to go. So cooling becomes essential. During the Apollo missions, astronauts wore liquid-cooled garments beneath their suits. Thin tubes carried water around the body, absorbing heat and transporting it away from the skin. This warmed water was then routed to systems that could release that energy into space through radiation. Without this system, overheating would occur quickly. But outside the suit, conditions shift with extreme contrast. On the surface of the moon, where there is no atmosphere to distribute energy, a single rock can reach 127 degrees Celsius in direct sunlight. Move just a few meters into shadow, and that same surface can drop to negative 173 degrees Celsius. Both conditions exist side by side. There is no gradual transition between them, no blending of temperatures. Each surface responds only to whether it receives sunlight or not. Without air, there is no mechanism to smooth out these differences. The same pattern appears in orbit. The International Space Station circles Earth at an altitude where sunlight and shadow alternate rapidly. Its structure faces direct solar radiation on one side, while the opposite side remains in darkness. Surfaces exposed to sunlight heat up, while shaded areas cool dramatically, sometimes reaching negative 157 degrees Celsius. But the station itself does not simply freeze or overheat. It uses a thermal control system built around circulating ammonia, a fluid chosen for its ability to absorb and release heat efficiently. This coolant moves through loops, collecting excess heat from equipment and crew areas, then transferring it to large radiator panels that emit the energy into space as infrared radiation. This balance must be maintained constantly. But the most unexpected detail remains with the human body. In an unprotected vacuum, you would not freeze instantly. That familiar image does not hold under closer examination. Without a medium to carry heat away, your body would initially retain its internal energy, warming rather than cooling. Only over time, through radiation alone, would heat gradually be lost. So the environment outside is intensely cold, yet the absence of air prevents that cold from acting quickly. At the same time, direct sunlight delivers energy without moderation. Two extremes exist together. And survival depends not on resisting cold alone, but on managing heat in a place where both burning and freezing can occur at once. Close to us, there is a place where these principles play out without interference. The moon orbits just beyond Earth's atmosphere, yet its environment behaves in a completely different way. It has no atmosphere and no global magnetic field to shield or distribute incoming energy. What arrives from the sun meets the surface directly. A lunar day lasts about 14 Earth days, meaning one side of the moon faces continuous sunlight for nearly 2 weeks. During this long exposure, the surface absorbs energy steadily, with no clouds, air, or circulation to moderate the process. Temperature rises without interruption. At peak conditions, the surface can reach around 127 degrees Celsius. The ground holds that energy as long as sunlight continues. But when night falls, the change is immediate and absolute. Darkness lasts another 14 Earth days. Without sunlight, the surface begins to lose energy through radiation alone. There is no atmosphere to retain heat, no convection to redistribute it, no insulating layer to slow the loss. Temperatures drop to negative 173 degrees Celsius across the same terrain. A single surface experiences a swing of about 300 degrees. There is no weather here, no wind, no movement of heat across regions. Each point on the surface responds only to its exposure to sunlight or its absence. The pattern is stark and consistent, repeating with every lunar cycle. But the effects do not extend deeply. During the Apollo 17 mission in 1972, astronauts placed heat flow probes into the lunar soil. These instruments measured how temperature changed with depth beneath the surface. The results showed that solar heating penetrates only a few meters into the regolith, the loose layer of dust and rock covering the moon. Below that shallow layer, temperatures remain stable. The surface absorbs and releases energy, but the interior stays largely unaffected by these extreme swings. Heat does not travel far without a medium to carry it inward. There are places where sunlight never reaches at all. Near the lunar poles, certain craters are permanently shadowed due to the angle of the sun's light. Their interiors have remained in darkness for billions of years. Without direct radiation, these regions cool continuously until they approach negative 250 degrees Celsius, close to the lowest natural temperatures measured in the solar system. In these frozen conditions, water ice can persist. Observations have confirmed that ice exists within these craters, preserved over immense timescales because no heat has ever reached them. There is no mechanism to deliver energy into these regions, and so they remain locked in a stable, cold state. The moon reveals something essential. Solar energy does not spread evenly through space or across surfaces. It acts where it arrives, and only there. Each location responds independently, shaped entirely by direct exposure. Between the sun and the moon, the vacuum remains unchanged. Energy passes through it continuously, yet it does not accumulate or transform into warmth. The surface heats, the shadows cool, and the space between them stays as it is, unaffected by the exchange happening at either end. Leave the sun behind far enough, and its influence fades into absence. Within the solar system, there is still a trace of outward energy, a thinning presence that shapes conditions in subtle ways. But between stars, that trace disappears. Interstellar space begins where local effects end. Here, the medium consists of sparse gas and dust spread across distances measured in light years. At first glance, it might seem empty, but it contains particles moving at significant speeds. In some regions, especially where gas is ionized, meaning atoms have lost electrons and carry charge, temperatures can reach around 10,000 Kelvin. That sounds intense, but temperature alone does not tell the full story. A single particle moving rapidly can be described as having a high temperature, yet it carries almost no energy in practical terms. What matters for heat is thermal energy density, the amount of energy contained within a given volume. In interstellar space, that density is extremely low. There are simply too few particles. So even though individual atoms move quickly, they rarely collide. Without frequent interactions, energy is not transferred effectively. A spacecraft passing through such a region would not experience significant heating despite the high measured temperature of those particles. But not all regions are alike. Within vast molecular clouds, composed mostly of hydrogen molecules, conditions are very different. These clouds are denser by interstellar standards, though still incredibly thin compared to anything on Earth. Their temperatures can fall to around 10 Kelvin or negative 263 degrees Celsius. These are among the coldest stable environments in the galaxy. Yet within them, something begins. Over millions of years, gravity slowly pulls the gas inward. As density increases, regions within the cloud collapse, eventually forming new stars. These clouds act as stellar nurseries, places where cold allows structure to develop before heat returns through fusion. Cold enables formation. There are even more extreme cases. The Boomerang Nebula, located about 5,000 light years from Earth, holds the record for the coldest known natural temperature in the universe. Its temperature has been measured at approximately 1 Kelvin, even lower than the cosmic background. This happens because the nebula is expanding rapidly. As gas expands, it does work on its surroundings, losing internal energy in the process. That loss results in further cooling, pushing its temperature below the baseline set by the surrounding universe. So cold can deepen under the right conditions. But this landscape is not uniform. Interstellar space contains regions of varying temperature shaped by local processes, density, and motion. Some areas hold energetic particles moving quickly, others remain near the lowest possible limits. Each region reflects a balance between energy input and the tendency toward dispersion. But across all of it, one pattern holds. Warmth appears only where matter gathers or processes concentrate energy. Everywhere else, energy spreads thin, interactions become rare, and temperature approaches the lowest levels allowed by the universe. Between stars, cold is not an exception. It is the background against which everything else briefly stands out. Consider a simple container designed to keep a drink warm. Inside its walls, a small gap holds almost no air. This device, often called a vacuum flask, relies on the absence of matter to slow the loss of heat. Between its inner and outer layers, particles are largely missing. Without particles, conduction cannot occur. There are no atoms touching across the gap to pass energy along. Convection also fails because there is no fluid to circulate and carry heat away. The only remaining pathway is radiation, which moves energy slowly compared to the other two. This is why a hot liquid can remain warm for hours. But even this engineered vacuum is not perfect. A tiny amount of residual gas remains, often around 1,000th of normal air pressure. That small presence still allows some energy transfer, reducing the overall insulation over time. Space is far more empty. In interplanetary regions, the number of particles is so low that even the best laboratory vacuums cannot match it. This near total absence of matter makes space an almost ideal insulator, preventing heat from spreading through contact or motion. So energy cannot fill the void. When the sun emits radiation, it travels outward without interacting with the vacuum itself. There is nothing there to receive or distribute that energy. The space between objects does not warm because there is no mechanism to carry heat across it. This leads to an important idea. Thermal equilibrium describes a state where objects reach the same temperature as their surroundings through continuous energy exchange. On Earth, this happens naturally because molecules are constantly colliding, sharing energy until differences even out. In space, that process changes. With no surrounding medium, an object can only exchange energy through radiation. It emits energy outward as infrared waves, gradually losing its internal motion. Over time, it approaches the temperature of the background radiation that fills the universe. That level is about 2.7 Kelvin. Without any nearby star or energy source, an isolated object in deep space will continue radiating away its heat until it settles near this baseline. The process is slow because radiation alone transfers energy far less efficiently than conduction or convection. The absence of matter extends the timeline. Imagine placing a cup of hot coffee in deep space, far from any star. It would not cool in minutes, as it does in open air. Instead, it would lose heat gradually, taking years or even decades to approach the background temperature. There is no breeze to carry warmth away, only a steady, quiet emission of energy. So the vacuum does not act as a sink that pulls heat out rapidly. It acts as a barrier that prevents heat from moving easily at all. Energy leaves only through radiation, and that pathway is slow and limited. But given enough time, the outcome is inevitable. Without continuous input, every object drifts toward the same cold baseline, not because something removes its heat aggressively, but because nothing replaces what is lost. And in a universe defined by emptiness, that loss continues until only the faintest motion remains. Engineers design for an environment that will not help them at all. Without air, there is no passive cooling, no gentle exchange with surroundings, no steady balance forming on its own. Every spacecraft must carry its own solution, shaping how it gains and loses energy moment by moment. Some missions must stay extremely cold. The James Webb Space Telescope operates in infrared, detecting faint heat signatures from distant galaxies. If its instruments warmed above about 50 Kelvin, they would begin to emit their own infrared radiation, overwhelming the signals they are meant to observe. To prevent this, the telescope uses a large sunshield made of 5 thin layers, each reflecting and radiating energy away. The shield spans an area comparable to a tennis court. Each layer faces the sun and deflects incoming radiation while also releasing absorbed energy back into space. This creates a temperature gradient, meaning a gradual change in temperature across the layers. On the sunward side, temperatures can reach around 85 degrees Celsius. On the shaded side, they fall to roughly negative 233 degrees. The telescope remains in the cold behind it. But not every mission needs to avoid heat. Far from the sun, the challenge reverses. Spacecraft begin to lose energy steadily through radiation, with no external source to replace it. In these regions, systems must generate their own warmth to remain functional. Voyager 1, now more than 23 billion kilometers from the sun, relies on radioactive decay to produce heat. It carries plutonium-238, a material that releases energy as it decays over time. This process provides a small but steady source of heat and electricity, keeping instruments operational in deep space. The energy is limited but consistent. Closer to home, Mars rovers face a similar problem during the long nights on the Martian surface. Temperatures can drop to around negative 125 degrees Celsius. To survive, these machines use radioisotope heater units, small pellets of radioactive material that emit heat continuously, protecting batteries and electronics from freezing. Thermal design becomes a balance. Too close to the sun, and systems must shed excess energy. Too far, and they must conserve or generate it. In many cases, both conditions exist simultaneously on different parts of the same spacecraft. One side may face direct sunlight, the other remains in shadow. This contrast requires careful control, using reflective surfaces, radiators, insulation, and active circulation systems to manage energy flow. Every surface is designed with purpose, determining how much energy it absorbs, reflects, or emits. But the most extreme case moves closer still. The Parker Solar Probe approaches within about 6.2 million kilometers of the Sun's surface. At that distance, incoming radiation is intense. To survive, the spacecraft uses a carbon composite heat shield about 11.4 centimeters thick. The front of the shield faces temperatures near 1,400 degrees Celsius. Behind it, the instruments remain near room temperature. This separation is not achieved by removing heat through air, but by controlling how energy is absorbed and radiated. The shield reflects much of the incoming energy and emits what it absorbs back into space, preventing it from reaching the spacecraft interior. In this environment, survival depends entirely on design. There is no natural balance to rely on. Every degree of temperature must be managed, every surface carefully considered, because in the absence of air, energy moves only by the rules we have already traced. Step back far enough, and even a star becomes small. The observable universe spans about 93 billion light years in diameter, a scale so large that familiar distances begin to lose meaning. Against that backdrop, the reach of a single star is limited in ways that are not immediately obvious. The sun's energy spreads outward in every direction, but its influence does not extend indefinitely in any practical sense. There is a region around the sun where its radiation can still be detected above the background, a fading sphere of influence that stretches perhaps 2 light years at most. Beyond that, its energy becomes indistinguishable from the faint radiation already present everywhere. The signal dissolves into the noise. The nearest star system, centered on Proxima Centauri, lies about 4.24 light years away. By the time sunlight travels that far, it has spread so thin that its contribution becomes effectively zero. It arrives, but it does not matter. Distance removes impact without removing presence. Within our own galaxy, the Milky Way, there are estimated to be between 200 and 400 billion stars. Each one generates energy, forming its own small region of influence. Yet between these stars lies vast empty space, regions where radiation from any one source becomes diluted beyond significance. The pattern repeats on larger scales. Galaxies themselves are separated by millions of light years, each surrounded by immense volumes of near-empty space. Even when considering the combined output of all stars across the observable universe, the average energy density remains extremely low. Energy exists everywhere. It is just spread too thin. Most of the universe, more than 99.9999% of its volume, contains almost no matter and receives negligible radiation from any nearby source. These regions are not actively cooled. They simply never receive enough concentrated energy to become warm. This is where a deeper principle emerges. Entropy describes the tendency of a system to move toward disorder and equilibrium. In simple terms, energy spreads out, differences even out, and concentrated structures become less defined over time. In a universe dominated by empty space, equilibrium does not mean warmth. It means uniform cold. Heat requires gradients, differences between hot and cold regions that allow energy to flow. But as energy disperses across larger volumes, those gradients weaken. Without concentration, there is no sustained warmth. The sun, powerful as it is, contributes to this process rather than opposing it. Every photon it emits spreads outward, becoming part of a larger distribution. It does not gather or accumulate at a universal scale. It dilutes, joining the vast background where individual contributions lose distinction. So the sun is not failing to heat space because of a lack of energy. It is because the scale of the universe ensures that energy cannot remain concentrated for long. On human timescales, the sun feels dominant. On cosmological timescales, its influence is brief and local. The outcome is already determined. In a system this large, where space vastly outweighs matter, equilibrium favors the state that requires the least concentrated energy. And that state is cold. Follow a single photon long enough, and it never truly arrives. It leaves the sun's surface and moves outward, passing planets, drifting beyond dust, continuing through regions where nothing interrupts its path. Most photons released by the sun never strike anything at all. They keep going. Each one carries energy set at the moment of emission. For a time, that energy remains unchanged as it crosses space. But the universe itself is not static. It expands, stretching the fabric through which light travels. As space expands, wavelengths stretch with it. This process is called redshift, where light shifts toward longer wavelengths, reducing its energy. A photon that began as visible light can gradually move into infrared, then into microwave, and eventually into wavelengths so long that their energy becomes extremely low. The photon is still there, but its ability to transfer meaningful energy fades. Given enough time, measured in trillions of years, these photons become so stretched that they no longer contribute to heating anything in any practical sense. Their energy has not vanished, but it has been diluted beyond usefulness. It becomes part of a larger background. This background includes the same faint radiation we described earlier, the residual energy spread across the universe. As more photons from stars join this field, they blend into it, adding to a pool of energy that continues to cool as expansion progresses. Nothing is lost. Everything is spread. The sun has been releasing energy for about 4.6 billion years. Every photon it has ever emitted still exists somewhere, traveling through space or contributing to this diffuse background. None of it has disappeared, but its effect has changed completely. If you could gather all the energy the sun has ever released and distribute it evenly across the observable universe, the resulting increase in temperature would be immeasurably small. The sheer volume of space ensures that even vast amounts of energy become negligible when spread thin enough. Scale dominates outcome. This is not an abstract idea or a poetic description. It is a direct consequence of thermodynamics, the study of how energy moves and changes form. Energy is conserved, meaning it cannot be created or destroyed, but it can be redistributed, diluted, and transformed into states where it no longer performs useful work. That is what happens here. The universe absorbs energy not by holding it in one place, but by dispersing it across ever larger distances. Each photon contributes to a gradual leveling, reducing differences in energy between regions. But as those differences fade, so does the ability to generate heat. Heat depends on gradients, on contrasts between higher and lower energy states. As energy spreads evenly, those contrasts disappear. What remains is a uniform field where no significant transfer occurs. So the sun's energy does not accumulate in space. It enters a process of continual spreading, joining a background that becomes colder over time. Expansion ensures that even this background continues to lose energy density. The direction is consistent. Energy moves outward, stretches, and blends into the larger whole. And across vast timescales, the universe trends toward a state where that energy remains present, but no longer capable of warming anything at all. In the quiet between interactions, every object is still doing something. Even when nothing seems to move, energy continues to leave. This happens through a process called black body radiation, the emission of energy as electromagnetic waves from any object with a temperature above absolute zero. Nothing needs to be touched. Nothing needs to flow. As long as particles have motion, they emit radiation. The amount and type of radiation depend on temperature. Hotter objects emit energy at shorter wavelengths, meaning higher energy radiation. Cooler objects emit longer wavelengths, carrying less energy but still following the same process. This relationship shapes what we can see. The surface of the sun, at about 5,500 degrees Celsius, emits most of its radiation in the visible range. That is why it appears bright to our eyes. Its energy falls within the narrow band that human vision can detect. But cooler objects behave differently. Earth, with an average surface temperature near 15 degrees Celsius, emits radiation mostly in the infrared range. This radiation carries energy, but it lies beyond the limits of human sight. We do not see it, yet it is constantly leaving the planet. The same applies to you. The human body emits infrared radiation as well. Your skin, warmer than the surrounding environment, continuously releases energy outward. Thermal cameras detect this emission, translating it into visible images that reveal temperature differences. So even in stillness, energy is always moving away. But this process extends beyond individual objects. The cosmic microwave background itself is an example of blackbody radiation. It represents the cooled remnants of the early universe, now stretched into microwave wavelengths through expansion. Its uniform glow fills all of space, marking the lowest energy level that remains measurable. Everything participates in this process. Every surface, every particle system, every structure above absolute zero emits radiation according to its temperature. This emission does not require interaction with other matter. It happens independently, driven by internal motion alone. But there is a limit. At absolute zero, where particle motion would cease entirely, blackbody radiation would stop. With no motion, there is no energy to emit. This defines a true boundary, a state where energy transfer through radiation no longer occurs. Nothing colder is possible, but nothing naturally reaches that state. Instead, objects approach it gradually. They lose energy through radiation, cooling over time, but never fully eliminating motion. The process slows as temperatures drop, but it continues as long as any energy remains. This creates a steady trend. Everything radiates. Everything loses energy. Over time, without external input, temperatures fall, not abruptly, but through continuous emission into surrounding space. But space does not return that energy in equal measure, so the balance always favors loss. Across the universe, this process repeats at every scale. Stars radiate intensely, planets radiate more slowly, smaller objects lose energy over longer periods. Each contributes to a broader pattern where energy disperses and temperatures decline. The universe, in this sense, is always cooling. Not because energy disappears, but because it spreads, becomes less concentrated, less able to produce heat, and through black body radiation, every object plays its part in that gradual shift. There is a layer around Earth that quietly changes everything. It is not thick by planetary standards, yet it alters how energy moves in ways that space cannot replicate. This layer, the atmosphere, does more than receive sunlight. It reshapes how that energy stays. Incoming light passes through it with little resistance. Visible wavelengths from the sun move through atmospheric gases and reach the surface, where they are absorbed and converted into motion. But when that energy leaves again, it does not return in the same form. The surface emits infrared radiation, longer wavelengths that behave differently when they meet the air. Certain gases respond strongly to this outgoing energy. Water vapor, carbon dioxide, and methane are known as greenhouse gases. They are largely transparent to incoming sunlight, allowing energy to reach the surface. But they absorb infrared radiation emitted by the ground, then re-release it in all directions. Some of that energy returns downward. This repeated exchange slows the loss of heat to space. Energy remains within the lower atmosphere longer than it would otherwise, creating a stable range of temperatures suitable for liquid water and complex systems. Without this effect, the outcome would be very different. If Earth had no greenhouse gases, its average surface temperature would be about negative 18 degrees Celsius. Large portions of the planet would remain frozen, and the balance we experience would not exist. But this mechanism does not operate at a fixed strength. Consider Venus. Its atmosphere is composed of about 96% carbon dioxide, forming a dense envelope that traps outgoing radiation almost completely. Surface temperatures reach around 465 degrees Celsius, making it hotter than Mercury, even though Mercury is closer to the Sunday. Distance alone does not determine temperature. Venus shows that an atmosphere can dominate the thermal behavior of a planet, amplifying the effects of incoming energy far beyond what distance would suggest. Now look at Mars. It orbits farther from the Sun than Earth, but still receives a measurable amount of solar radiation. However, its atmosphere is thin, unable to retain much of the energy that reaches its surface. As a result, average temperatures hover near negative 63 degrees Celsius. Energy arrives, it does not stay. Across these three worlds, a pattern emerges. Earth, Venus, and Mars exist within a similar region of the solar system, yet their surface conditions differ dramatically. The key difference is not their distance from the Sun, but how their atmospheres handle energy once it arrives. Atmosphere controls retention, but beyond these planets, there is nothing comparable. Space has no gases to intercept outgoing radiation, no medium to absorb and re-emit energy. Photons that leave a surface continue outward without returning. There is no cycle, no delay, no mechanism to hold warmth in place, so energy escapes freely. Any object exposed to space must rely on its own properties to manage heat. Without an atmosphere, there is no shared system to stabilize temperature. The contrast is clear. Where atmosphere exists, energy can circulate and remain. Where it does not, energy moves on, leaving surfaces to cool. And in that absence, the universe returns to its default condition, one where heat cannot be trapped and cold steadily prevails. Between planets, there is more than nothing, yet far less than something. This region, called the interplanetary medium, contains a scattered mixture of particles, fields, and dust. It is not a true void, but it remains so thin that its presence is easy to misunderstand. Particles move through it constantly. The solar wind fills this space with charged particles, while magnetic fields stretch outward from the sun, shaping their motion. Occasional atoms drift between them, remnants of processes that began closer to the star. All of it exists in motion, yet none of it forms a continuous substance. This leads to an unusual property. The interplanetary medium can be described as having a temperature, sometimes reaching values near 100,000 Kelvin in certain regions. This measurement refers to the speed of individual particles, not to a shared thermal state like the air around you. Fast particles, few collisions. Without density, temperature loses its usual meaning. A single particle moving rapidly carries energy, but with so few neighbors, it rarely transfers that energy to anything else. A spacecraft moving through this environment does not heat up significantly because interactions are too infrequent to matter. Energy exists, but it is not exchanged. Among these sparse particles, there is also dust. Cosmic dust grains, often only a few micrometers in size, drift through interplanetary space. They are composed of silicates and carbon-based materials formed from earlier generations of stars. Unlike isolated particles, these grains can absorb sunlight and re-emit it as infrared radiation. They have measurable temperatures. This dust creates a subtle visual effect. Along the plane of the solar system, known as the ecliptic, faint light can sometimes be seen just before sunrise or after sunset. This glow is called zodiacal light, produced when sunlight scatters off interplanetary dust particles. It is a quiet signal, but as distance increases, even these traces begin to fade. Moving outward from the sun, the density of particles drops further, the solar wind weakens, dust becomes less common, magnetic influences diminish. Each factor reduces the ability of this medium to interact with passing objects. Conditions grow simpler. By the time you reach the Kuiper Belt, a region extending roughly from 30 to 50 astronomical units from the Sun, the environment has thinned to the point where solar influence becomes minimal. Objects here receive very little energy, and temperatures settle near negative 220 degrees Celsius. Further out, the trend continues. On Pluto, which orbits within this distant region, surface temperatures average around negative 233 degrees Celsius. Despite still being within the sun's reach, the available energy is too sparse to produce significant warming. The pattern remains consistent. The interplanetary medium is not empty, but it is not capable of carrying or sustaining heat in any meaningful way. Its particles move, its dust absorbs and emits energy, yet its overall density prevents these processes from combining into anything that resembles warmth. So energy passes through it, with little effect. The closer you are to the sun, the more noticeable its influence becomes. The farther you go, the more that influence fades, leaving behind a region that approaches the same quiet baseline found throughout the wider universe. Some stars end not with a gentle fade, but with a collapse so intense that matter changes its nature. When a massive star exhausts its fuel, its core can compress under gravity until protons and electrons combine into neutrons, forming an object only about 20 kilometers across, yet containing more mass than the Sunday. This is a neutron star. At birth, its temperature exceeds 100 billion degrees Celsius. Energy is trapped within an incredibly dense structure where particles are packed so tightly that familiar states of matter no longer apply. But this heat does not linger in the way we might expect. Cooling begins immediately. In the first million years, neutron stars lose energy primarily through neutrino emission. Neutrinos are nearly massless particles that interact very weakly with matter, allowing them to pass through dense regions almost without resistance. They carry energy away at speeds close to that of light, removing heat from deep within the star. The loss is rapid at first. As time passes, the dominant cooling process shifts. The surface begins to radiate energy outward as electromagnetic waves, including X-rays produced by the still extreme temperatures. After millions of years, a neutron star can cool to around 1 million degrees Celsius. Still intensely hot, yet already diminished. Over much longer timescales, the cooling continues. One of the coldest known neutron stars, PSRJ 214433933, has an estimated surface temperature near 42,000 degrees Celsius. It is ancient by stellar standards, isolated, slowly releasing its remaining energy into surrounding space. But even at these temperatures, its influence is limited. The radiation it emits spreads outward, thinning rapidly as distance increases. There is no surrounding medium to retain or distribute that energy. The heat leaves the star, but it does not accumulate in the space around it. The pattern holds. Even the most extreme concentrations of energy cannot overcome the dispersing nature of the vacuum. Heat radiates away, becoming less concentrated with every passing moment. This process is not unique to neutron stars. White dwarfs, the remnants left behind by stars like our Sun, begin their existence at temperatures around 100,000 degrees Celsius. Without fusion to sustain them, they gradually cool over immense periods, radiating energy into space. The timeline stretches far beyond human comprehension. Over trillions of years, white dwarfs will continue to lose energy, becoming cooler and dimmer until they reach a state known as a black dwarf. At that point, they no longer emit visible radiation, existing as cold, dark remnants. But none exist yet. The universe is not old enough for any white dwarf to have cooled that far. Every one we observe still carries residual heat from its earlier state, slowly releasing it into the surrounding vacuum. So even in these extreme cases, the outcome remains consistent. Energy is produced, concentrated, and then dispersed. No matter how intense the initial conditions, the surrounding space does not retain that heat. It allows it to pass, to spread, to dilute, and over time, even the hottest remnants follow the same path, moving steadily toward the same quiet baseline that defines the rest of the universe. In a controlled chamber, far from any natural environment, temperature can be pushed beyond what the universe provides on its own. Not by removing heat in the usual sense, but by slowing motion with extraordinary precision. In 2018, an experiment aboard the International Space Station reached a temperature of 38 picokelvins. That is 0.0000000000038 Kelvin, far below the natural background of space, colder than anything known to occur naturally. This was achieved using the Cold Atom Lab, a facility designed to study matter at extremely low energies. Its goal is not simply to cool objects, but to reduce the motion of individual atoms to nearly complete stillness. The method relies on light. Laser cooling uses photons directed at atoms moving toward the source. Each photon carries momentum, and when it strikes an atom, it slows the atom slightly. This process is repeated continuously, billions of times per second, reducing the overall motion of the atomic system. Motion decreases, temperature follows. But reaching such low levels requires more than repeated interactions. It also requires isolation from gravity's effects. On Earth, atoms in a cooling trap fall under their own weight, limiting how long they can be manipulated. In orbit, microgravity allows atoms to remain suspended, extending the time available for cooling. This environment enables new states of matter. At temperatures this low, atoms begin to behave in ways that do not appear under normal conditions. One such state is called a Bose-Einstein condensate, where individual atoms lose their distinct identities and act as a single quantum entity. Their behavior becomes unified. Instead of moving independently, they occupy the same energy state, forming a collective system that can be described with a single wave function. This reveals properties that are hidden at higher temperatures, where thermal motion dominates. The system becomes coherent. But this achievement also shifts perspective. For most of the universe, the lowest temperature is set by background radiation. Natural processes rarely push below that level. Yet here, in a carefully controlled setting, humans have created conditions colder than that baseline, an inversion of expectation. Instead of observing what the universe provides, we have engineered a state that goes beyond it. Not by changing the laws of physics, but by applying them with precision, removing energy in ways that natural systems cannot easily replicate. But the significance is not limited to extremes. Cold becomes a tool. By reducing motion, scientists can observe interactions that are otherwise masked by thermal activity. Subtle forces become measurable. Quantum behaviors become visible. Systems that seem chaotic at higher temperatures reveal underlying order. Precision increases as motion decreases. So, cold is not simply the absence of heat. It is a condition that allows deeper observation, where the smallest interactions can be studied without interference from random motion. In the broader context, this experiment mirrors the same trend seen throughout the universe. Energy disperses, motion slows, systems approach lower states. But here, that process is guided deliberately, and in doing so, it reveals that cold is not only a destination, it is also a method for understanding everything along the way. Look at a map of the universe, and it does not appear random. Galaxies gather along long filaments, clusters form at intersections, and between them stretch enormous voids where almost nothing exists. This pattern, often called the cosmic web, emerged from a subtle balance between heat and cold in the early universe. At the beginning, there was no structure like this. For the first 380,000 years, the universe existed as a hot plasma, a state where electrons and nuclei moved freely without forming stable atoms. In this phase, radiation and matter were tightly coupled, meaning energy and particles interacted constantly, preventing any lasting separation. Everything was mixed, but as expansion continued, temperatures dropped. Eventually, conditions became cool enough for electrons to bind with nuclei, forming neutral atoms. This event, known as recombination, marked a transition where matter and radiation could begin to behave independently. Light could move freely. With radiation no longer scattering constantly, matter was left to respond primarily to gravity. Small variations in density, already present at this stage, began to matter. Regions with slightly more mass exerted slightly stronger gravitational pull. The differences were tiny. Measurements of the cosmic microwave background show temperature variations on the order of 100,000th of a Kelvin. These minute fluctuations, detected by missions such as WMAP and Planck, reveal how uniform the early universe was, yet also how small imbalances existed within it. Those imbalances grew. Gravity amplified them over millions of years. Slightly denser regions attracted more matter, increasing their mass and strengthening their pull. Over time, these areas collapsed further, eventually forming the first stars and galaxies. Structure emerged from imbalance. As matter gathered into filaments and clusters, other regions were left behind. These became cosmic voids, vast spaces spanning hundreds of millions of light years with extremely low density. In these regions, there are few stars, few galaxies, and very little interaction. They remain nearly unchanged. Without significant sources of energy nearby, these voids retain conditions close to the baseline set by the background radiation. Their temperatures are uniform, lacking the variations caused by local heating. In many ways, they represent the closest approximation to the universe's default state. Cold defines them, but this cold is not simply emptiness. It is the condition that allowed structure to form elsewhere. Without cooling, matter would have remained too energetic to clump under gravity. Without slight temperature differences, there would have been no regions of preference, no seeds for growth. Variation was essential. The interplay between expansion, cooling, and gravity created a framework where matter could gather in some places and disperse in others. Filaments formed where density increased. Voids expanded where density remained low. The pattern persists. Even today, galaxies trace these ancient pathways, following structures shaped billions of years ago. The distribution of matter reflects the earliest conditions, preserved through time. So, cold is not just what fills the gaps, it is what allowed the gaps to exist and what made the clusters possible. Without it, there would be no contrast, no structure, no large scale pattern to observe. The universe's architecture is written in temperature, and the quiet regions between galaxies reveal that cold is not an absence, but the foundation on which everything else was built. Time itself carries a direction, and in the universe, that direction leads toward lower energy. Not because heat disappears, but because it spreads, stretches, and becomes less concentrated with every passing moment. Expansion is the key. Since its earliest state, space has been growing, increasing the distance between every region. As space expands, it affects everything moving through it, including light. Photons traveling across the universe experience a stretching of their wavelengths, a process known as redshift. Longer wavelengths mean less energy. This effect can be traced directly through the cosmic background radiation. When it was first released, its temperature was about 3000 Kelvin, over 13.8 billion years. As the universe expanded by a factor of roughly 1,100, that temperature has fallen to about 2.7 Kelvin. The cooling is not accidental. It is built into the expansion itself. As distances grow, energy density decreases. Radiation becomes more diffuse, less capable of producing measurable heat. The background temperature continues to drop, following the same trend that has defined the universe since its beginning. But radiation is not the only factor. Stars also shape this process, though their influence changes over time. The rate of star formation across the universe reached its peak around 10 billion years ago. Since then, it has been steadily declining as available gas is consumed or dispersed. Fewer stars are forming now. Given enough time, this trend leads to an endpoint. In about 100 trillion years, the last stars will exhaust their nuclear fuel. Without new stars forming to replace them, the era of luminous objects, known as the stelliferous era, will come to an end. Light fades gradually. What remains are stellar remnants. White dwarfs, neutron stars, and black holes persist, each containing energy that continues to radiate away over immense timescales. These objects do not remain static. They cool, emit, and slowly lose their stored energy. Even black holes are not permanent. Through a process called Hawking radiation, they release energy over time, shrinking gradually. This process is extremely slow, taking periods far beyond the current age of the universe, but it follows the same principle. Energy disperses. As these remnants continue to lose energy, the universe moves toward a state where no significant sources of heat remain. Temperature differences diminish. Energy becomes evenly distributed, leaving no gradients to drive change. This state is called heat death. It does not mean high temperature. It means equilibrium, where every region reaches nearly the same low energy level, just above absolute zero. In this condition, no work can be done. No structure can form. No process can extract usable energy. Everything settles. The path to this state is gradual but consistent. Expansion stretches radiation. Stars burn out. Remnants cool. Energy spreads thinner and thinner across an ever-growing volume. But nothing interrupts the trend. The universe does not cycle back to higher energy. It continues forward, following the direction set by expansion and entropy. Every process contributes to the same outcome, a steady movement toward uniform cold. At the far edge of time, change becomes impossible, not because energy is gone, but because it is everywhere, evenly spread, leaving no direction for anything to move or transform. This is what physicists call heat death. The term can sound misleading. It does not describe a universe filled with heat, but one where temperature is uniform across all space. Thermal equilibrium means every point shares nearly the same, extremely low energy level. No gradients remain. The idea was first explored in the 19th century by Lord Kelvin and Hermann von Helmholtz, building on the second law of thermodynamics. This law states that entropy, often understood as disorder or the spreading of energy, always increases in a closed system. The universe is such a system. Over time, energy moves from concentrated forms to dispersed ones. Differences even out. Hot regions cool. Cold regions warm slightly if energy reaches them. But as expansion continues, the dominant effect is dilution, not balance through mixing. Eventually, there is nothing left to equalize. In a state of maximum entropy, no usable energy remains. There are no stars to produce light, no planets with temperature differences, no chemical reactions capable of sustaining complexity. Without gradients, no work can be performed. Everything becomes static. The timescale for this outcome is immense. Estimates suggest around 10 raised to the power of 100 years, a number so large it exceeds ordinary comprehension. It extends far beyond the current age of the universe, which is about 13.8 billion years. But the direction is already set. Dark energy, the unknown force driving the acceleration of cosmic expansion, continues to push galaxies apart. As distances increase, matter becomes more isolated. Radiation stretches further. Energy density decreases steadily. Separation grows. Over these vast spans of time, even the smallest remnants lose energy. White dwarfs cool, neutron stars fade, black holes evaporate through quantum processes. Each step reduces the amount of concentrated energy available. Nothing reverses the trend. What remains is a universe that is cold, diffuse, and uniform, not empty, but lacking the differences required for change. Temperature approaches a value just above absolute zero, with no regions standing out from the rest. No contrast, no motion that matters. But this final state also reveals something fundamental. The universe did not begin this way. It started hot and dense, with energy packed into a small volume, capable of driving rapid change. Over time, expansion transformed that condition into the opposite, spreading energy across an ever larger space, from concentration to dispersion. So the question that began this journey shifts. Space is not cold because something removed its heat. It is cold because the universe evolves toward that state. Heat appears only where energy gathers, where conditions allow it to concentrate temporarily. Every star, every warm surface, every source of energy is part of that temporary phase. And in the long arc of time, those phases pass, leaving behind the uniform condition that the universe has been moving toward since the beginning. On this planet, there is a narrow band where matter behaves in a way life can use. Water remains liquid between 0 and 100 degrees Celsius at standard pressure, and within that range, chemistry becomes flexible enough to support complex systems. Outside it, options collapse quickly. Liquid water freezes into rigid structure below that range, and above it, it turns to vapor, breaking the continuity required for stable reactions. Life, as we know it, exists inside this thin window where motion and structure balance each other. That window is not guaranteed. Around every star, there exists a region where temperatures allow liquid water to persist on a planetary surface. This region is called the habitable zone, a narrow band defined by distance, radiation, and planetary conditions. It is small compared to the system around it. Earth occupies a position near the center of this zone, at a distance shaped by billions of years of orbital evolution. Small variations in distance would shift conditions significantly, altering how much energy reaches the surface. The balance is precise. Nearly all of the energy driving Earth's climate comes from the sunday. About 99.97% of the energy sustaining the biosphere originates from solar radiation. The remaining fraction comes from geothermal sources, heat stored within the planet from its formation and radioactive decay. Without the sun, that balance disappears. If solar input were removed, Earth's surface temperature would drop to around -18 degrees Celsius within weeks. As stored heat radiated away, temperatures would continue to fall, approaching -80 degrees within a year. The system would collapse into cold. What we experience as a stable environment depends entirely on continuous energy input from a nearby star. That energy maintains motion, drives atmospheric circulation, and supports the chemical reactions that define living systems. Life borrows its warmth. This dependency extends beyond Earth. Across the universe, planets exist in vast numbers, orbiting stars at a wide range of distances. But only a small fraction occupy positions where conditions allow liquid water to exist on their surfaces. The requirements are strict. Distance must be within a narrow range. Atmospheric composition must support energy retention without excessive heating. Surface conditions must allow stability over long periods. Many systems do not meet these conditions. Even within the estimated hundreds of billions of trillions of stars in the observable universe, only a fraction host planets within habitable zones, and fewer still maintain the additional factors required for life. The rarity becomes clear. Warmth is not the default state. It is a temporary condition that emerges when energy is concentrated in the right place, under the right conditions, for the right duration. But beyond these regions, the universe returns to its baseline. Cold dominates the vast majority of space. It surrounds every star system, extending in all directions, unchanged by local exceptions. The warmth that supports life exists within a narrow boundary maintained by a single energy source. And outside that boundary, the same quiet cold remains, waiting, unchanged, across distances far greater than any region where life has taken hold. Across the sky, there are more worlds than we once imagined. As of 2024, more than 5,600 exoplanets have been confirmed, each orbiting a distant star under conditions that vary in ways both subtle and extreme. They are not rare anymore. Some circle close, scorched by intense radiation. Others drift far out, receiving only a faint trace of light. Between these extremes, there are systems that resemble our own, though never quite the same. One of the most studied lies, 40 light-years away. The TRAPPIST-1 system contains 7 Earth-sized planets tightly packed around a small red dwarf star. 3 of these worlds sit within the region where liquid water could exist, depending on their atmospheres and surface conditions. The geometry is compact, but the physics is unchanged. The space between that star and its planets remains a vacuum, governed by the same rules we experience here. Energy travels outward as radiation, interacting only when it meets matter, leaving the vast regions between bodies largely untouched. Cold persists there as well. Not all planets remain bound to a star. Some are cast out during the chaotic early stages of planetary formation, ejected by gravitational interactions that send them drifting into interstellar space. These are called rogue planets. Without a nearby star, their surfaces fall toward temperatures around negative 240 degrees Celsius. In the absence of external energy, they cool steadily, radiating away what little heat they possess. They become isolated worlds. But internal processes can still play a role. Some of these planets may contain radioactive elements within their interiors, slowly releasing heat through decay. This energy can maintain subsurface layers of liquid water beneath thick ice shells. Warmth, in this case, comes from within. It is limited and hidden. Observations have also revealed planets with extreme cold, even within star systems. One example, discovered through gravitational microlensing in 2005, is OGEL 2005 BLG 390 lb, a world with an estimated surface temperature near negative 220 degrees Celsius. Its nickname reflects its nature. Cold dominates its environment despite the presence of a host star, because distance and conditions prevent significant warming. The balance between energy received and energy lost defines its state. This pattern repeats across observations. Each system forms its own localized pocket of warmth, shaped by distance, composition, and stellar output. But beyond those pockets, the surrounding space remains largely unchanged, extending outward into regions where energy becomes too diffuse to matter. The contrast is consistent. Heat appears only where it can be sustained. Everywhere else, the universe returns to its baseline condition, a quiet, persistent cold that fills the spaces between stars. And as we look outward, across thousands of these distant systems, the same rule continues to hold. Warmth is confined, dependent, and temporary, while the cold between them stretches on, unchanged, across distances that no single star can overcome. If we imagine removing cold from the story, the universe becomes unrecognizable, not darker or quieter, but unstable, unable to hold structure long enough for anything to endure. Heat alone cannot build. In the earliest stages of star formation, vast clouds of hydrogen drift through space, diffuse and extended across light years. Gravity begins to pull these clouds inward, compressing the gas as density increases. But compression raises temperature, and rising temperature pushes back outward. The collapse would stall there. For a star to form, the cloud must lose energy as it contracts. This happens through radiation, energy escaping into surrounding space, allowing the cloud to continue shrinking. Cold, in this sense, is not absence, but permission for gravity to proceed. It enables structure to begin. As stars live and die, they create heavier elements through nuclear processes, forging carbon, oxygen, silicon, and iron in their cores. When these stars explode or shed their outer layers, those elements scatter into space as hot, expanding gas. But they do not remain that way. They cool. As temperature drops, atoms slow and begin to bond, forming dust grains and complex molecules. Without cooling, these elements would remain too energetic to combine, never assembling into the materials that form planets or bodies. Cold allows matter to settle. It shapes the aftermath of creation. Even the faint background glow we measure across the sky depends on this cooling. The cosmic microwave background exists because the early universe expanded and cooled enough for atoms to form, allowing light to travel freely. Without that transition, there would be no clear signal. The universe would remain opaque. Cold made it readable. At smaller scales, the role of cold becomes even more precise. Certain physical phenomena only emerge when thermal motion is reduced to extremely low levels. One example is superconductivity, a state where electrical resistance drops to zero, allowing current to flow without loss. This occurs only near absolute zero. Another is the Bose-Einstein condensate, first produced in 1995 by Eric Cornell and Carl Wieman. In this state, atoms slow so completely that they begin to behave as a single quantum entity, losing their individual identities. Motion becomes collective. These states are not possible in warmth. They require stillness, but the pattern remains consistent across scales. Heat drives motion, initiates change, and creates new structures. Cold allows those structures to stabilize, persist, and evolve into more complex forms. Creation and preservation work together. One without the other fails. The universe does not oppose cold, it depends on it. Every star, every planet, every molecule that has formed did so because energy could be released, because temperature could drop, because motion could slow enough for structure to hold. Cold is not the absence of activity. It is the condition that makes lasting order possible. And within that condition, complexity finds a way to remain, long enough for the universe to become more than a momentary burst of energy, shaping itself into something that endures. There was a moment in March 1965 when a human body first entered the open vacuum and discovered something unexpected. Alexei Leonov drifted outside his spacecraft, suspended above Earth, surrounded by silence that carried no air and no sense of familiar temperature. The cold did not behave as expected. Inside his suit, heat began to build. Without air to carry it away, his own body warmth accumulated, raising internal pressure as the suit expanded slightly. Movement became difficult, and returning to the capsule required careful effort under conditions no one had fully experienced before. The danger was not freezing, it was overheating. This pattern has defined every spacewalk since. When you leave the protective boundary of atmosphere, you do not enter a uniformly cold place. You enter a system where temperature depends entirely on exposure and control. Astronauts manage this constantly. During operations in sunlight, they rotate slowly to distribute incoming energy across their suits. This controlled movement, sometimes called a rotisserie roll, prevents one side from absorbing too much radiation while the other remains in relative shadow. Balance must be maintained. Even in orbit, the transition between light and shadow is abrupt. As a spacecraft passes into Earth's shadow, the temperature of exposed materials can drop rapidly. Metal contracts measurably, responding to the sudden loss of incoming radiation. These shifts are precise. They are predictable, but they must be accounted for. The systems that support human presence in space are built around this reality. Spacecraft use circulating fluids, radiators, and reflective surfaces to manage internal heat. Excess energy must be removed carefully because there is no surrounding medium to absorb it through contact or flow. Everything is engineered. Every surface is designed with temperature in mind. But the experience is not only physical. Astronauts often describe looking outward into the darkness and sensing the cold as something more than a measurement. It is not felt directly, but perceived as a constant backdrop, an absence that defines the environment beyond the thin barrier of the suit. The contrast is immediate. Inside, controlled warmth. Outside, unchanging cold. Human presence in space depends on maintaining that boundary. Life support systems preserve pressure, supply oxygen, and regulate temperature within a narrow range that the body can tolerate. Without these systems, the environment beyond offers no gradual transition. It does not adapt. We adapt to it. This necessity has given rise to an entire field of engineering focused on thermal control. Every spacecraft, from early capsules to modern stations, must manage the balance between absorbing energy and releasing it. Too much heat, and systems fail. Too little, and they cease to function. The challenge is constant. We carry our conditions with us. Each mission extends a small, controlled environment into a place that does not support it naturally. Within that environment, warmth is maintained, not because space provides it, but because we design systems to preserve it. And beyond that boundary, the same vast cold remains, unchanged, surrounding every human presence with a silence that does not respond, waiting just beyond the reach of the thin layers that keep us alive. If we step back from everything we have followed, a pattern settles into place. It is not dramatic at first glance, but once seen, it becomes difficult to ignore. Warmth is the exception. Across the universe, the baseline condition is not heat waiting to spread. It is cold waiting to remain, unless something actively resists it. That resistance takes form only when matter gathers densely enough, when gravity compresses it, when energy is released faster than it can escape. That is when heat appears. Stars are the clearest example. They exist because gravity forces hydrogen together until nuclear fusion begins, releasing energy that pushes outward against collapse. This balance sustains them, but only for a limited time. Nothing holds forever. Planets with atmospheres extend this balance further. They intercept incoming radiation, redistribute it, and retain part of it long enough to maintain surface conditions that remain stable over time. Living systems, in turn, depend on this stability, drawing on constant energy input to sustain ordered processes. But each layer depends on the one before it. Remove the source, and the structure fails. Entropy, defined as the tendency of systems to move toward disorder and uniform energy distribution, works continuously in the background. It does not rush, it does not pause. It simply ensures that concentrated energy spreads out over time. Heat dissipates, cold remains. Even the sun, which has burned for billions of years and will continue for billions more, exists on a timescale that is brief compared to the broader lifespan of the universe. Its remaining lifetime, about 5 billion years, is a short interval when set against durations that extend far beyond any familiar measure. A moment, in context, this reframes how we understand warmth. It is not a permanent feature of space. It is a temporary state that arises under specific conditions, maintained only as long as those conditions persist. It must be sustained. Every warm object you encounter, from a star to a living body, is actively managing energy. It absorbs, transforms, and releases it in a continuous cycle that prevents equilibrium with the surrounding environment. Because equilibrium is cold, the space beyond these systems does not need to cool further. It already rests near the lowest possible energy state, shaped only by faint background radiation that has persisted since the early universe. That is the default. Against that backdrop, each instance of warmth becomes something unusual, a region where energy remains concentrated, where gradients exist, where processes can occur that would otherwise fade into stillness. But these regions are limited. They are bounded by distance, time, and available energy. As photons travel outward, as stars age, as structures evolve, the ability to maintain these gradients diminishes. And yet, within those boundaries, something remarkable happens. Energy arrives, interacts, and is absorbed. A photon meets a surface, transfers its energy, and becomes part of a system that continues, briefly, to resist equilibrium. A small interruption, a temporary condition, but one that, for a time, allows structure, complexity, and experience to exist within a universe that otherwise settles, steadily and without urgency, back toward the quiet persistence of cold. If you pause for a moment and look upward, the distance between you and the wider universe is thinner than it feels. Above you, the atmosphere rises and fades, becoming so sparse that within roughly 100 kilometers, the familiar rules of warmth begin to loosen. Beyond that, the baseline returns. The air that carries heat, the medium that softens change, disappears. What remains is the same quiet condition that has existed since the universe first cooled enough for light to move freely, long before planets formed or stars settled into their current shapes. Cold waits there. It does not move closer. It does not retreat. It simply remains, unchanged, just beyond the boundary that surrounds you. Everything you have experienced, every surface you have touched, every current of air and shifting season has taken place within a narrow layer where energy is held and shared. This layer is not thick on cosmic terms. It is a thin shell wrapped around a single world, maintained by a continuous flow of energy from a nearby star. That flow never stops. Every moment, radiation arrives, interacts, and becomes heat when it meets matter. It warms oceans, drives winds, and sustains the processes that allow complex systems to continue. Without that constant input, the balance would shift quickly. But it has not. Across the span of human history, through every era and every change, the warmth has remained steady enough to support continuity. Cities have risen and fallen under its influence. Ecosystems have adapted within its range. Each generation has lived within the same narrow thermal window, rarely needing to consider how limited it truly is. It feels permanent, but it is not. The star that provides this energy will not burn forever. Like all stars, it exists within a finite lifespan, converting mass into energy at a rate that cannot be sustained indefinitely. The process continues for billions of years, but even that duration is brief when placed against the wider scale of cosmic time. Eventually, it will change. The balance will shift, but that moment is distant. For now, the system holds. The energy continues to arrive, and the conditions required for warmth remain intact. Within this small region, against the broader backdrop of cold, processes unfold that depend entirely on that ongoing input. Life continues. And if you consider where that energy originates, the scale becomes clearer. A star, roughly 150 million kilometers away, is converting about 600 million tons of hydrogen into helium every second, releasing energy that travels across space and reaches this planet in a steady stream. All of this to maintain a thin layer of warmth. A small interruption in a vast cold, but it is enough. Enough to sustain oceans, atmospheres, and the countless interactions that define a living world. Enough to keep the balance in place, for now, within a universe that otherwise settles quietly towards stillness. And as this continues, as the energy arrives again with each passing moment, the same simple condition remains true. You are here, within that narrow band, held in warmth surrounded by cold, while something distant continues, steadily and without pause, to keep the lights on.